Solder is one of the oldest known methods of joining metals. The ancient Egyptians used solder to bond and mend pottery. Stained glass windows in many early cathedrals were made with solder. Eventually, it became regarded as a highly reliable bonding agent for certain metals. Today, solder is the subject of exact scientific study and analysis. Cost per joint, initial investment, ease of automation, and serviceability are prime factors that make solder superior to other methods of joining metals. It provides electrical continuity, and we use it to bind together the hundreds of small components that make our products work. Being one of the oldest, simplest, and most widely used metals in the world, it has often been taken for granted. But to do its job, solder must be applied properly. To use solder effectively, it'll help you to know more about it. Technically, solder is a non-ferrous, fusible, metallic alloy. It is not a glue, but a filler material. When melted, it joins metal surfaces. The solder used in electrical assembly is simply a mixture of tin and lead. It is usually specified by the percentages of tin to lead, with tin given first. The 6337 or eutectic solder used for electrical assembly has 63% tin and 37% lead. Eutectic solder is the strongest of all tin-lead solders. The tensile strength and shear strength of solder is dependent on the ratio of tin to lead in the alloy. The melting point of solder depends on the percentages or ratios of the two metals in the alloy. A pure metal always melts at a single temperature. Tin melts at 449 degrees Fahrenheit, or 232 degrees Celsius, and lead melts at 621 degrees Fahrenheit, or 327 degrees Celsius. Notice the melting point of eutectic solder is many degrees lower than that of tin or lead. It melts at 361 degrees Fahrenheit, or 183 degrees Celsius. Here is a combination of two metals that for some reason will melt at temperatures much lower than the two metals it is made of. No one can tell you exactly why this happens. 50-50 solder, for example, melts at 421 degrees Fahrenheit, 216 degrees Celsius, but it does not solidify until it cools to 361 degrees Fahrenheit, or 183 degrees Celsius. Eutectic SN63, on the other hand, melts at 361 degrees Fahrenheit, 183 degrees Celsius, and solidifies at the same temperature. The range between the melting temperature and the solidifying or setting temperatures in all tin-lead solders except eutectic have a pasty consistency or plasticity. Let's look at an example and see how solder works. Here is a sheet of pure lead and a rod of pure tin. Both have relatively low melting points, but through the miracle of solder they are bonded together without the danger of melting the tin or the lead. For example, the seams of an ordinary tin can are soldered together without damaging the tin. Now let's look a little more in detail and see how it makes this bonding effect. Notice that on this sheet of copper, as the solder melts, it flows smoothly to form a thin, even coating. When the copper was hot enough to melt the solder, the molten solder actually dissolved small amounts of the copper and then penetrated its surface. In this cross-sectional drawing, we can see that the molecules of the two metals have actually blended together here to form one new metal, which is part solder and part copper. This mixing of the molecules is called the wetting action. To obtain good wetting action is not always simple. When a clean metal surface is exposed to air, a chemical reaction called oxidation occurs. When heat is applied, as in a soldering operation, the oxidation is greatly speeded up and produces a non-metallic film that would prevent solder from touching the base metal. This film of oxidation makes good wetting action impossible. So even though our metal has been cleaned thoroughly beforehand, The oxide in these areas formed while we heated the copper and prevented the solder from bonding. These oxides must be removed or prevented during the solder operation. For this, we use non-corrosive natural rosin fluxes. Never use acid flux core solder because it is very corrosive and can damage solder connections. For ease of application, the solder and flux are produced in a combination called core solder. The rosin flux is contained in the solder itself. With this cutaway model of cored solder, we are able to see exactly how the solder flux combination can work together. The flux must have a melting point lower than that of solder, thus enabling the flux to reach the metal first and prepare the way for the solder. As the solder melts, it displaces the flux on the clean surface and helps solder flow as it should. Then the flux rises to the top and is pushed to the outer edges, carrying with it the oxide it has removed. After cooling, this action stops. Rosin flux residues don't conduct electricity. This removes the danger of shorting out connections where the flux has flowed between them. It is good practice to remove the flux residue after soldering. This eliminates the chance of the residue collecting harmful dust particles and leaves a clean, neat connection. With the continued trend towards miniaturization in electronics, there has been a considerable reduction in size of the solder joint, joint members, and the tools and equipment used in hand soldering production. Because of this trend, it is even more important to produce a clean, mechanically sound bond between joint members. The integrity of the solder joint is closely related to not only techniques in soldering, but also the choice and condition of production and maintenance tools. Let's look at the solder tool in more detail. In any solder operation, a heat source is needed. Conduction-type soldering irons are the most commonly used heat source. The conduction-type soldering iron consists of a few simple parts. The cord passes through the handle to a heating element, which in turn transmits the heat to the tip of the iron. An 18 to 25 watt iron is generally used for heat-sensitive and small electronic components. A 40 to 65 watt iron is used for large terminals and fasteners. Where more heat is necessary, larger tips and higher wattages are required. This is a cross-section view of a plug-type iron-plated soldering tip. The center core is high-purity copper, chosen for its high thermal conductivity. The machine copper form of a soldering tip is electroplated with 6/1000ths to 30/1000ths of an inch, or .150 millimeter to .762 millimeter thick layer of pure iron. The working area of the tip is tinned by the manufacturer, and the remaining surface protected from corrosion by nickel plating and subsequently immunized by chromium plating, which prevents solder from wicking up the shank of the tip. In general, iron plating on copper is the best structure for a soldering tip, and because pure iron is dissolved in molten tin at a slower rate than pure copper iron plated tips, last from 20 to 50 times longer than pure copper tips, and they require no filing or reshaping. When pure copper tips are used in soldering, the copper surface is rapidly dissolved in molten tin and will require reshaping as often as every half hour. The basic design of a soldering iron determines the soldering tip shank design. The two most common types of soldering tip shank designs are the plug type and the slotted sleeve type. The plug type shank is secured in a heating well where the heating element surrounds the soldering tip shank. The shank is straight where it is retained in the heating element by a set screw. The problem of set screw seizing caused by oxide corrosion of the threads is a common one. Daily inspection of the soldering iron with the tip removed before and after each operator shift is good maintenance practice. Scale should be removed from the heating element and the tip shank. If the tip shank is badly worn or excessive contamination is built up and not easily removed, replace the tip with a new one. Remember, when the tip is difficult to remove, you should never give the iron a physical shock because the heating element could be damaged. The sleeve-type shank completely surrounds the heating element mandrel and is rarely troubled with removal problems caused by corrosion. The sleeve is slotted to allow crimp retention by the spring clip. The sleeve permits the soldering tip to absorb heat from the heating element by conduction and radiation. The selection of the size and shape of the solder tip is the most important decision because any soldering job will be easier when you select the proper tip. Most manufactured tips are work rated, and you can easily compare a particular tip shape with the work characteristics you need. The tip size must be large enough to permit efficient heat transfer from the iron heater to the connection. A tip smaller than the connection cannot possibly do an efficient job of transporting heat. A tip larger than the connection will result in damage to adjacent circuitry and will be difficult to place on the connection accurately. When selecting the size of the tip, the shape must also be considered. The shape of the tip should permit the greatest contact possible with the connection being soldered. Before you begin soldering, be sure the tip is well tinned with solder. This is a simple process. For a new or reworked tip, wrap several turns of solder around the tip face of a cool soldering iron. As the iron heats up, the solder will melt and coat the tip face. Then spread the molten solder evenly over the tip face by gently wiping it on a wet sponge several times. Normal use will produce a buildup of oxides and dirt on a used tip. Simply applying rosin core solder to the used tip is another method of continuous tinning of the iron. Also, this coating of solder on the tip greatly increases the transmission of heat from the iron to the work. Tinning keeps the tip clean, which is imperative for a clean connection. When a soldering iron is removed from its holder, the operator should first clean the soldering tip on a wet, sulfur-free industrial cellulose sponge. The wet sponge provides a thermal shock to break free and remove secondary oxides of tin and lead from the tip's surface. The best cleaning sponge for this purpose is a vertical segmented rotary sponge held in a non-corrosive container. The tip is passed between the vertical segments of the sponges, which exerts a uniform and repeatable cleaning action each time it is used. Notice that the operator also rotates the soldering iron as it is pulled through the sponges. The rotary sponges revolve during the cleaning process and provide a fresh, clean sponge area for subsequent cleaning. In addition to this, the collection of solder dross, which is excessive solder and flux that remains on the sponge after the tip is cleaned, tends to drop in its holding base. This permits the operator to use the sponges a number of times before a thorough cleaning is required. A flat sponge, rags, or metal brush accumulate contamination and after being used for a period of time present the risk of transferring this contamination to the solder joint. The wiping or cleaning action and pressure will usually vary between different operators when the tip must be cleaned on a horizontal cleaning surface. Excess wiping is likely to result in detinning, and different habits of different operators will often result in different detinning rates if the tips are not properly tinned after each cleaning or use in making one or several solder joints. After cleaning, the point tip of the solder iron is tinned with rosin core solder. When the solder joint is very small, the tinning procedure is often omitted. The operator then depends on the residual solder left on the tip to make wetted contact with the joint members. The cleaned and tinned iron tip is placed on one side of the connection point and fresh rosin core solder on the opposite side of the joint members away from the hot iron tip. This procedure ensures the iron tip will heat the connection point, which in turn will heat and melt the applied rosin core solder. The solder will heat relatively slowly, around 500 degrees Fahrenheit or 260 degrees Celsius, and melt and flow around the joint. Remember, for good wetting action, the metal to be soldered must be as hot as molten solder. For this reason, we heat the joint and then apply rosin core solder. It is the connection point that actually melts the solder. When soldering, never apply solder to the iron. If solder is applied directly to or adjacent to a hot soldering iron tip, it'll probably carbonize or burn away the rosin flux before it's able to thoroughly clean the joint members. At the solder melting temperature, the rosin flux chemically cleans the connection. This removes oxide contaminants, permitting a metallurgical bond between the tin, molten solder, and the joint members. Besides cleaning, the rosin flux adds to the fluidity of the molten solder, improving the wetting action. Surface tension of the molten solder is reduced, allowing it to flow more freely. An iron with the proper size and wattage heats the joint members almost instantly, so the application of the iron and then the solder is almost simultaneous. It should be realized that excessive pressure or rubbing a tip on a joint will not improve heat transfer, but might damage the iron plating or bend the soldering iron tip. Heat transfer can best be improved between the connection point and the iron tip by increasing the tip's wetted contact area with the joint members. Wire crimped into a circuit board or wrapped around a terminal doesn't constitute a solid connection. The two metals are not actually touching. A film of oxidation holds them apart, but the action of the molten solder makes them perform as one solid metal. As the solder melts, it blends with the other metals, forming a permanent bond. Once the molten rosin core solder flows around the joint members, remove your iron and solder immediately and allow the connection to cool a few seconds undisturbed. How you hold your tip, the wattage of the iron, and various other factors determine how long it takes to make a good solder connection. Usually, a good solder joint is made in 2 seconds or less. Tin the working surface of a soldering tip with rosin core solder and return the soldering iron to its holder. Failure of the operator to do this protective step causes degradation of the tip and decreases tip life. When proper soldering procedures are not followed, a tip will detin or de-wet, making it useless to the operator. Degradation, the start of oxidation of the tinned areas, is evident when the solder tends to ball up on the tip. Once a tip begins to detin, the action will continue until the tip is no longer wet with fresh solder and only makes a dry contact. When this happens, the tip is no longer an efficient heat source. Again, detinning can be avoided if the tip is tinned with rosin core solder after each soldering operation and prior to placing the solder iron in its holder. Although 98% of detinning problems depend on operator care, there are other causes. These can be excessively high idling temperature, bad solder, or bad flux. All too often, a detinned soldering tip is discarded. This is costly and usually unnecessary. A detinned tip is the result of the formation of a tenacious crust of primary oxides on what was originally the tinned surface of an iron-plated soldering tip. This heavy oxide cannot be broken free by thermal shock and mild cleaning action on a wet sponge. But restoration can be done in a short time, either by the operator or someone designated in the assembly area. The recommended procedure is to remove the soldering tip from the hot iron and let it cool. Then, with a piece of 100 grit emery cloth obtainable from central stores, remove the scaly oxides and polish the tip. Next, wrap rosin core solder around the cleaned surface as in normal tinning. To enhance and accelerate the cleaning and tinning process, dip the iron tip in rosin flux. Finally, heat the tip, and when the solder melts, flood the tip with plenty of rosin core solder until the tip appears fully restored. A word of caution: never file an iron-plated soldering tip. A file will not only remove oxides, but most, if not all, of the iron plating will also be removed. This shortens the life of the tip dramatically. To keep iron-plated tips long-lasting and maximize performance, solder at the lowest practical temperature. Keep the soldering tip properly tinned at all times. As you may recall, solder is not a glue, but a filler material. It is not used to secure strength. Any solder joint is weaker than the base metals that are joined. Therefore, no mechanical or structural requirements should be put on solder. Where possible, parts should be mechanically joined before soldering. To add solder to a connection after adequate wetting has taken place is of no value. One of the greatest causes of unsatisfactory solder joints, especially for beginners, is excessive solder. Essentially, it is a good hot solder joint, but with such a buildup of solder that the contour of the component lead or wire can't be seen. Beads of solder project from the joint members, and the joint usually has the appearance of a blob. The primary cause is in applying too much solder too fast to the connection. Tip size in relation to the joint size, too large a diameter solder, and too hot an iron temperature are other factors affecting joint quality. The right amount of solder is a necessary requirement for an acceptable solder joint. An acceptable solder joint has both a shiny appearance, indicating that the flowing action was hot enough to be smooth, and the correct amount of solder, revealing the contour of the mechanical wrap or connection. Too much heat will cause the solder to appear gray because of carbonizing of the rosin flux. This can easily be mistaken for a cold solder joint, so it is always advisable to leave the soldering iron tip on the joint members only long enough to make the rosin core solder flow completely around the joint. Never cook the connection. Only apply enough solder to cause proper alloying action. At solder melting temperature, a slight concave fillet should form between the joint members. The contour of the part should be visible after soldering. This form of soldering, called contour soldering, has several advantages that makes its use desirable. Not only is it possible to use less solder, make good-looking connections, and exhibit fine workmanship, but in contour soldering, defects are more easily spotted. The other extreme is where the rosin core solder doesn't completely cover the connection or joint area. Molten solder must flow freely over the surface of a metal to have a good wetting action. With too little solder on the joint, a good solder-to-metal bond cannot take place. Insufficient solder on the joint can cause the connection to rupture due to stress, vibration, and fatigue, leaving the joint non-functional. It's important for you to learn to apply the correct amount of solder on a joint and determine if the joint meets quality and reliability standards. It's also important for you to recognize faulty connections and be able to correct them. The cold joint, the rosin joint, and the fractured joint are the most common kinds of bad connections. A cold joint results when rosin core solder doesn't get hot enough to flow freely around the joint members. De-wetting occurs, exhibiting an abrupt rise of the solder from the surface. Usually this happens when the soldering iron is removed too soon, or the metals to be soldered are not thoroughly clean. Oxides build up on the joint members, preventing alloying action. Cold joints are chalky in appearance and lack a metallic luster. This can be eliminated by properly cleaning the joint members and soldering at solder melting temperature. A rosin joint develops when rosin flux gets trapped in the solder. Insufficient soldering temperature and remnants of the cold joint don't let the rosin core flux escape as the solder begins to flow. The soldering iron is removed too quickly and a rosin pocket forms. Electrical and mechanical integrity of the joint members is seriously impaired. The components or wires are held together by rosin residues. Rosin joints can be avoided by proper application of rosin core solder, iron temperature, and the amount of time the tip is in contact with the connection. The rosin core solder should be fed slowly to the joint members while the soldering iron is providing sufficient heat to melt the solder and bring the rosin to the surface of the connection. Remove the soldering iron as soon as it is apparent the rosin flux has been dislocated from within the connection and the molten solder has adequately wetted the joint. One easy test for this type of joint is to see if the part moves under light probing pressure. All too often, quality problems relate to haste. Fractured joints usually occur because operators are hurried and accidentally jar the joint members before the solder has completely hardened. The disturbed joint will have an irregular, dull, rough, gritty appearance. The surface will generally show cracks or strain marks. Mechanical bonding and electrical continuity are destroyed. Care should be taken not to disturb or jog a connection until the solder has solidified. When you don't get a satisfactory connection, take the joint members apart. Any reheating or resoldering should be avoided. The joint members must be thoroughly cleaned and the entire soldering operation repeated. At this point, we would be remiss if we didn't discuss desoldering or unsoldering. Occasionally, completed electronic assemblies must be reworked or modified to accompany design changes or faulty components. When this happens, parts must be unsoldered and removed. Typically, there are three methods of desoldering. First, the simplest and easiest method of desoldering is by heating the connection so that the solder melts enough to remove the part. Care must be taken not to drop solder on the circuit board or allow solder to fly at you. For safety, it is well to always wear protective glasses when either soldering or desoldering. This method of desoldering is acceptable only if no new components or wires are to be added to the connection. By reheating the joint, you cause new oxides and residues that cannot be easily removed unless you induce fresh rosin core solder, and then you risk the chance of excessive solder buildup on the joint. To develop a quality and reliable connection, it is generally always best to completely remove the old solder and resolder with fresh rosin core solder. The second and most widely accepted method of desoldering is called wicking. Wicking is the flow of molten solder by capillary action. This can best be done by using a piece of wire-braided material that is impregnated with rosin flux. Several companies manufacture a wicking braid and supply it in various sizes and lengths. Apply the tinned iron to the braid as close as possible to the joint. The braid should be between the iron and the joint members. As the braid heats up, the molten solder is drawn in by capillary action. You may have to move the braid a time or two for complete absorption of the solder from the joint. It's most important to remove the braid and the soldering iron simultaneously by sliding them off and away from the connection. Care should be exercised not to overheat the joint, for the circuit board could be damaged or the pad around the component could be lifted from the board. The third method of solder removal is used where a large quantity of solder is to be removed from a circuit board. This method utilizes the advantage of vacuum principles, either created or induced. Two types of vacuum systems are employed. They are the solder pull and semi-automatic desoldering system. The solder pull tool is the most widely used. It is inexpensive and relatively easy to use. Two kinds of solder pull tools are the syringe type and the spring-loaded or extractor type. The syringe type is nothing more than a bulb or reservoir with a connecting hollow tube. Heat the joint with a soldering iron and opposite the iron squeeze the bulb and place the syringe as close as possible to the joint without touching it. When the solder around the joint is at molten temperature, quickly release the bulb, allowing it to expand to normal size. The molten solder will be drawn into the bulb reservoir. As soon as this is done, remove the iron and syringe. After you have desoldered several joints, it's necessary to remove the bulb from the syringe and clean out the old solder. The solder pull or solder sucker, as it is more commonly called, is used pretty much in the same way as the syringe type. The tool utilizes a spring-loaded plunger in a barrel to create a temporary vacuum for solder removal. The trigger activates a spring-operated plunger. The cleaning shaft acts as a valve during the initial vacuum stroke. As the shaft leaves the tip orifice, a sudden high impulse force is created to lift the molten solder. Reloading the tool expels the old solder drawn into the orifice during the vacuum stroke. Like the syringe type, the tip life can be extended if you are careful not to press the tip orifice into the molten solder. Hold it only close enough to the solder to permit proper removal. Be careful not to inadvertently trigger the plunger until you are ready to do so, and you should always use the tool with care. In the semi-automatic system, a vacuum source provides a continuous suction. Removal is exactly like the syringe and solder pull methods. One advantage to this system, besides convenience, is you don't have to reload after each operation. The system is simple to operate and fast. Many boards can be desoldered in a day. This type of system is extremely useful where many joints must be unsoldered on a large scale or production environment and economics dictate justification. The techniques you use in soldering and desoldering are largely left up to you. Good techniques and vigilance are necessary to produce quality solder connections. In the final analysis, the principles you learned in this presentation will help you to do a better job.